Hi, you must have heard of the fact that equal polynomials must have the same corresponding coefficients. For example, if someone tells you that a polynomial with 3x squared plus 6x plus 4 is equal to another one with ax squared plus bx plus c, it implies that a equals 3, b equals 6, and c equals 4. But why they should be equal? Are we able to use other coefficients for a, b, and c while keeping the two polynomials equal to each other? In this video, we are going to see if the fact mentioned above is valid or not. Starting with two polynomials, fx and px, which have been told that they are equivalent and have the same degree, x to the nth power. In front of each term are the corresponding coefficients, an, bn, an minus 1, bn minus 1, etc. If the statement is correct, we should assume the result to be an equals bn, an minus 1 equals bn minus 1, and so on. We know that fx minus px, or in reverse order, px minus fx is equal to 0, since the two polynomials are the same. By simplifying the expression, we get to the equation an minus bn as a whole times x to the nth power, plus other terms with the power decreasing by 1, and eventually, a0 minus b0 is equal to 0. Let an minus bn be cn and the equation be gx. There comes an expression with a more straightforward version. By substituting 0 to the function, we have c0 equals 0. While z0 equals a0 minus b0, we can prove that a0 equals b0. To make life easier, we eliminate the last value, c0, from the equation gx, since we have already concluded that the last coefficients of the two polynomials are equal. If we divide gx by x, where x is a real number and is not equal to 0, we get to the expression where cn times x to the power of n minus 1, plus other terms, and finally plus c1, which equals 0. By moving c1 to the right-hand side of the equation, we use 0 minus the sum of the remaining terms, which the subtrahend can be referred to as s. When comparing the absolute value of s and the negative of this absolute value with c1, we can see that c1 is greater than or equal to the latter, but less than or equal to the former. However, as x approaches 0, both of the sides become 0. Thus, we can deduce that c1 equals 0 and a1 equals b1. By applying the same method to the remaining terms, we can prove that an minus 1 is equivalent to bn minus 1, an is equivalent to bn, etc. Since there is only one possible value for each corresponding term, fx is equal to px if and only if the coefficients of the corresponding powers are equal.